We will continue in this lecture the discussion of probability distribution, and we'll focus on the definition of probability and distribution for continuous variable, and we'll show how we can use function to describe them, and we'll introduce this concept called Galton machine and use it to illustrate how different distributions are related to one another. We'll now take a closer look at the difference between a discrete variable versus a continuous variable. We will continue our example from last lecture, x3 being the number of customers arriving in a bank in a 1 hour window, whereas x5 being time spent on an ATM machine, an ATM transaction measured in second. So if we use a number axis to represent valid values that a variable can take on, we notice that a discrete variable can only take on value that will be represented as a point on the time axis, whereas for a continuous variable, the valid value will cover a whole interval. For example, for x3, the valid value are represented as point here, each of these individual points, which are any positive integers. Whereas for x5, the valid values covers a wide interval like this. So this is always true for discrete versus continuous variables. And another way to look at the difference is by looking at how the value is calculated. For discrete variable, it could be considered as results from a counting process, whereas for a continuous variable, it's a result from a measuring process. And remember previously that we defined the probability for a discrete variable as a percentage, but the difference between the two types of variables we just discussed force us to define the probability for a continuous variable slightly differently, and we'll see why now. And since observe a continuous variable is to measure a quantity, and since all measurement devices have limitation in terms of accuracy, so when we say the last transaction took 45 seconds, we don't mean it's exact 45 seconds followed by infinite number of zero. Depending on the accuracy of the device you use, more likely we meant the time spent on the transaction is between an interval, and if the device we use is accurate down to the 8th decimals, then what we are really saying is the time spent in the last transaction is between 44.99999 second and 45.000001 second. Because the definition of a continuous variables, we notice that we can never be certain that an observed continuous variable is equal to an exact point value, and that is probability of x5 equal to 45 equal to 0. And the same is true for probability of x5 equal to any point in the number axis. And we can only speak of probability that observing a continuous variable falling into an interval. In other words, we realize that we will never be certain to observe a continuous variable to be equal to an exact point value. We describe mathematically p x equal to 45 or any point equal to 0. And therefore, we need to speak of probability for a continuous variable by the chance of it falling within an interval. Also realize that a continuous variable taking on any value being associated with 0 probability does not mean all intervals of same width are equally likely to occur. And let's use this following example to illustrate this point. So the probability of x5 equal to 10 is the same as equal to 45 equal to 0 because they are just 2 points. However, based on our experience, this is likely to be true, meaning the time spent between a small interval center at 10 seconds is less likely than the chance of time spent falling within this interval center at 45 seconds. Again, in other words, it's more likely to observe a transaction that takes around 45 seconds than to observe a transaction that takes around 10 seconds. And we can make similar statements but with a smaller interval. If this is true, then intuitively this is also true. The only difference being the interval is much smaller than the first example. And this intuitively, the former is still less than the latter for any small interval, no matter how infinitesimal it is. However, once the interval shrinks to a point, then the probability of both become equal to each other and equal to 0. We'll next talk about how to use function to describe probability distribution for a continuous variable. So in the 1895 paper, Carl Pearson, a founder of modern statistics, noticed that the problem we are dealing with probability distribution for continuous variable resembles another problem in mechanics. So in his paper, he borrowed a number of concepts from mechanics to use in describing probability distribution for continuous variable. And the problem he borrowed from in mechanics is about how to find the center of gravity for a piece of thin wood like this with irregular shape. The center of gravity along the x-axis is the point where you can put a finger underneath to balance this piece of wood. It's not going to be in the middle because this side of the wood is irregular. And the answer to that question requires the understanding of the weight distribution along this x-axis. We now look at why this problem resembles the probability distribution for continuous variable. The weight distribution along the x-axis. So if we want to speak of the weight at each point, then we have to realize that it will be 0 for any point, because we are talking about a slice of wood of 0 width. But if we increase the width of the slice from 0, say to 0.1, then we'll realize that the weight of this slice, which is center at x equal to 45 with plus and minus 0.1 width, will be heavier than that of x center at 10, because the height at 45 is higher than the height at 10. And this will remain true regardless of how small the width we are using. So this sounds almost exactly the same as the problem we were dealing with earlier with the probability distribution for continuous variable. So Carl Pearson borrowed a few concepts from mechanics to apply in model a continuous probability distribution. So in mechanics, the height is used to measure the density of the wood at each point along the x-axis. So Carl Pearson similarly defined a density function for each point of a continuous variable along the x-axis. In mechanics, the weight is calculated by measuring the area. Therefore, probability for continuous variable should also be measured as area. One difference between the two is, in mechanics, the weight of a piece of wood is not necessarily limited by a certain value. However, in statistics or probability, we do require the total probability to be equal to 1. Therefore, we need to find a density function so that the total area under the density curve, needs to be 1. We'll now look at how to use the density function to describe probability for a continuous variable. So let's say we find a density function to describe the x5, which is the time spent on an ATM transaction. So the first thing we know will be this being the density curve, then the area underneath the curve will equal to 1, which means the probability of a transaction takes on a value between 0 and the upper limit will be 100%. So if this area, the fourth segment, is 20% out of 100%, it means the probability of a transaction taking less than 10 seconds will be 20%. And here the second segment has the area of 0.25, which is 25%. It tells us the probability of time spent on a transaction between 10 seconds and 30 seconds is 25%. Also notice the definition, the meaning of this y-axis is no longer the probability, because as we know, the probability associated with each point value is always 0. And for the cumulative distribution function for a continuous variable is still defined in the same way, which is what is the probability of x taking on a value that is less than or equal to a particular value. And we can use this example to show how do we derive the cumulative probability for every single point in this x-axis. So if this segment is 20%, it means the probability of time spent on a transaction that is less than 10 seconds is 20%, which is the meaning of its associated cumulative probability. Therefore, if you find 10 in this axis, and then you should find the y value, the vertical value, to be 0.2, and similarly you can find the cumulative probability of 30 being the sum of these two segments, which should be 20 plus 25 equal to 45%. So in a similar fashion, you can find the cumulative probability for each point on this x-axis. And then once you plot them together as a curve, you would notice that this curve will eventually converge to 1. Finally, with the density function defined for continuous variable, we can also define the expectation for a continuous variable. But unlike in the discrete case where we use sum product to calculate it, for continuous case we will require calculus, and therefore we were not going to cover in this course. But the expectation of x for a continuous variable turned out to be the center of gravity along the x-axis for the piece of irregular wood that we introduced earlier. So now we will next turn to the Galton machine. So this is a video I found on YouTube about Galton machine. So Galton machine is a gadget invented by Francis Galton, another founder of modern statistics, to demonstrate a number of important principles in probabilities. So let's watch a little bit together. So I'm going to fast forward a little bit. I want to point a few things here. So if we call these tiny spherical object a bean, then we call these a pin, then the process of a bean bouncing off a pin is just like toss a coin. It will either go to the left or go to the right. And if the pin is perfectly round, then the chance of going to the left or going to the right will be 50% chance. And each level represent the next round of coin toss. So the whole process is a mechanical simulation of a binomial distribution. And notice that the final distribution is taking on a bell-shaped curve, and we can actually use Excel to simulate this mechanical device, and we can actually adjust the likelihood of going to the left or going to the right, and we can increase the number of levels to as many as we want. So this is an Excel worksheet that I designed to simulate the mechanical Galton machine with 30 levels and 1,000 beans poured down the machine. And I leave the probability of going left or right adjustable here. And as I said earlier, this Galton machine is an exact representation of a binomial distribution. In this case, pi equal to 0.5 and n equal to 30. But as we can see, if we increase the number of levels, we are increasing the possible value that a variable can take on. So it can actually be used to represent what we call the normal distribution, which is a distribution for a continuous variable. And the most distinctive feature of normal distribution is this bell-shaped curve. And also, if we change the probability of going to left or to the right to a different value, for example 0.25, we notice that the curve shift to the left, and we can continue decrease the probability to an even smaller number. And this shape is actually a shape taken by the Poisson distribution. And if we further reduce the probability to a even smaller percentage, and if we increase the level to a much higher number, it would actually take on a shape looks like this, which is known as an exponential distribution. So this is an example to illustrate the underlying relationship between many different distribution and many different shape of possible density function. And we'll leave it as an exercise to understand how this Excel simulation works. So this concludes our discussion on probability distribution.